we're going to publish a safety rating for this car, we need to know what the real numbers are. If we're going to publish the real numbers of fuel efficiency, we need to know what they are. And so they will drill down and do very intense, very long analyses to get what is going to actually result. And so instead of doing kind of a crash simulation with no dummy sitting in the seat or no mannequin in the seat, you'll see them doing crash analysis with a full load of mother, father, and children in the car, and asking the question, you know, is it still safe? Are they protected? If they're looking at the cooling inside of the car or the heating inside of the car, instead of it just being an empty compartment with no seats and things like that, the detailed analysis will have everything in there, including kind of the louvers on the vent. You know, is it just a straight open or is it an adjustable vent? They'll have all of that represented and be able to do some thermal flow analysis, cooling analysis inside of the car. This semester, we are not going to do any of the conceptual design work on the chassis, okay? So we're not going to ask you to do any kind of severe modifications to the design of your RC race car, the chassis, the powertrain. What we are asking you to do is what? Come up with individual designs for the shell. So you probably are going to do some sketching. You're going to look around at different car images. You're going to say, I really like this, I don't like this, I'm going to go very modernistic. You're going to do some conceptual design work for the body that you want to create to cover your RC race chassis. Okay? So there will be some of that sketching that you'll need to work on, and you'll need to be thinking about that, and you might as well start today. One person on your team should try to mimic the actual design of the car. So this car here is being used by the BYU Wayne State team. Who has that car? Which team? Have you guys decided yet who's going to try and do the 2010 body? Has that been assigned out or decided?
Not really. Our team is constantly growing, it seems.
Okay. You've got how many at Wayne State?
3.
You have 3, and you have probably one more added here.
We had 2 just added.
2 just added.
So we have 4 now.
Okay. So sometime soon, you're going to want to decide that, because that individual is, again, going to want to kind of decide sketch-wise how to make this thing look. But the rest of the team has to come up with their own look. Okay? The project is going to require an intense amount of collaboration. And we've awarded 50 points to the overall project to kind of focus on team collaboration. I know we've gotten off to a little bit of a rough start, but this bottom note here that says don't go more than a week without a meeting is very, very important. Ford, General Motors, when they're doing a car design, they have meetings 2 and 3 times a week. They don't let an entire week go by without a meeting, and so they're constantly getting the design team on and collaborating with them. So make sure that your collaboration is organized, it's focused, it's working well. The thing that we will begin talking about on Thursday is kind of the assembly parametrics, and it's based on creating lots of planes, lots of axes, lots of parameters, and those all exist in an assembly file, and then a certain set of those planes and lines are then replicated, linked down to part files, And when you open up a part file that has a plane and an axis in it, you can design your part based on that axis that gives you orientation, and the plane gives you position. And when you save your part off, because that file has linked to the assembly, if you open your assembly up, you would find that not only was the plane and the axis in the assembly part, but your finished part would automatically pop in where it needs to go. And so we're going to be using this assembly skeleton parametric approach to making this thing come together in a really elegant, robust way. We have a few people that have just joined, and it appears that your mic is still unmuted. If you could mute your mic, that would help. After we take a few lectures and talk about assembly parametrics, we're going to take a dive into topology optimization. Now I know that in labs 1, 2, and also in 3, we have you do some tutorials out of OptiStruct. OptiStruct is probably the best in class topology optimization tool that's sold out there in the market. Boeing uses it on every component in the 787. General Motors uses it on every significant component going into a new car. They try and figure out, can we get this part to be lighter and yet still withstand the load cases that are lighter. And so we are going to expect each of you to look at your car, decide some critical components. So maybe the main chassis is a critical component. You can design that as a design space, just a roughed out design space, and you can ask the computer to eat away all of the material that is not necessary, that's extra. And it would reduce that down, and what you would hope to find is a design very similar to what's already in your car. If it's significantly different than that, then go ahead and model a modified chassis for your car. Okay? So each of the things that are kind of been highlighted in the first few slides of this presentation have kind of a reoccurring theme in the project that we're doing here. Are we going to be doing part parametrics? Absolutely. The example given there in the upper right-hand corner is basically a cover, a head cover, and that thing is fully parametric so that you can say this is going on a 3-cylinder engine, this is going on a 4-cylinder engine. Okay? And they don't have to redesign it. The surface and solid modeling, that is going to be primarily where you're building the components out of solids and assembling them up. And the surface modeling is going to be primarily the shell, the exterior that you drop down over your car. Okay? We're not going to want any thickness to that. It can just reside as a surface. We will take time and action and ask you to do finite element of significant components. So things that have a significant amount of load placed on them, you'll do an FEA analysis of it. Hopefully they got it turned off. Not yet. Mass properties, we will do that on many of the individual components, and we will ask you to kind of calculate what your overall weight of your car is. And we're hoping that what you find is that the weight of an individual component as weighed by a scale is very close to the weight that the CAD system predicts it would be if you put in the right material properties. Okay? So as you're taking your car apart, think about just going in and finding an accurate scale, setting the part down, weighing it, using your calipers to measure the part, create it in CAD, and then when we get to the mass properties part of it, all you'll have to do is enter the material type, ask for it to calculate it, and then you'll be able to compare what the CAD system said to the actual weight measured by the scale. And hopefully, by the end of the semester, when you set the entire car on the scale and you ask for a full accounting of the mass properties of your CAD system, you'll be able to get that.
How many parts are we looking at modeling for each car?
Okay, so we're getting to that. There's a slide here that we're going to actually pull up and show you in just a minute and actually hopefully answer that question. We will do some on motion analysis, okay? So that is something that we want to have you look at and consider as part of the car. We will want you to consider and look at some CFD. Now the stuff that we do will be not the full body of the car. We'll just take a slice down through the car. So we'll take a planar cut and we'll do a 2D CFD analysis. But you will learn how to put on boundary layers. You'll learn how to set far walls, near walls, inlets, outlets. You'll learn how to set up the problem and do a basic solution of your car. Hopefully, by the end of the semester, you'll be able to generate a rendering of your vehicle that looks as nice as that image does. It's possible that is an image that came out of a CAD system. Okay? That's not a real car, that's an image. We hope at the end of the semester there will be enough time to have you take your shell, scale it down, and generate a rapid prototype of your little car. Okay. So now we want to talk about team organization. We have a BYU UBC team. We have a BYU Hornet team. The images on the left-hand side are the actual cars that they're working to. Hopefully, I got it right. I think I did. BYU UIA team, a BYU Sao Paulo team, a BYU Toluca team. Then we have a BYU Tongji team, a BYU NTU team. This is our CATIA team. There is another UBC Wayne State team, and they're still determining which car they want to go with. One of the faculty there is trying to encourage them to go with the Mustang. They like that. So, we've got a BYU only team, another CATIA team, and they're working on a Camaro. And then there's two UBC only teams, and they have this mini trophy truck